This is the video for section 6.1 to 6.4, which you are doing in the form of the simplifying radicals packet. So all I'm doing in this video is walking you through the packet and working the examples for you that I have worked already in the packet. So you'll get to hear my instruction as I work through the examples. So this is all about square roots and other roots. A square root of a number b is a solution of the equation x squared equals b. Every positive number has two square roots, which we would denote by the square root of b and negative square root of b. Or we can write them collectively as plus or minus the square root of b. It means we have the positive number and the negative number. We usually call the positive number the principal square root. That's usually the one we're interested in. But the other one exists, and we need to know that. So the square roots of 16 are positive 4 and negative 4. Since both 4 and negative 4 satisfy the equation x squared equals 16. 4 squared is 16. Negative 4 is also positive 16. The principal square root of 16 is positive 4. Since squaring a number will always result in a non-negative number, the equation x squared equals b has no real solutions if b is negative. Because there's no number I can multiply by itself and get a negative number. A positive number times itself is a positive number. A negative number times itself is a positive number, because a negative times a negative is a positive. So any negative number has no real square roots. So example A in this first part. Solve x squared equals 9. I'll show you two different ways to do it. The first way would be to do it the way we would have done this in the past. Is bring the 9 over so it's equal to 0. Factor the left-hand side, that's the difference of squares, x minus 3 times x plus 3, which means x equals 3 or x equals negative 3. So x equals, in a sense, plus or minus 3. Another way to do it is to say, well, the solutions to x squared equals 9 would be the square roots of 9. What are the square roots of 9? The square roots of 9 are 3 and negative 3. Okay? Part B, or example B, x squared plus 4 equals 0. I can try to factor that, but that's not a difference of squares, that's a sum of squares, and I know that I can't factor a sum of squares. I would have called that prime. So that tells me there's probably no real solutions. If I move the 4 to the other side, it becomes a negative 4, and then I can clearly see that there are no real solutions, because there are no real square roots of negative 4. Example C. 5x squared equals 15. I need it so that the x squared is by itself, so I need to divide both sides by 5. Okay, then I've got x squared equals 3. So I'm told that the solutions to that are going to be the square roots of 3. Well, what are the square roots of 3? The square roots of 3 are plus and minus square root of 3. And I stop there because 3 is not a perfect square, so its square root, while it's a real number, is an irrational number. I can't write it as a whole number. If I tried to factor this, I'd have x squared minus 3 equals 0. And previously we would have not called that a difference of squares, because we were factoring over the integers. But we could think of this as a difference of squares, where it's x minus square root of 3 times x plus square root of 3. And that would give us our two solutions. It is a difference of squares if we just take the square root of 3 as being plus and minus square root of 3. So then you have three problems to do that are just like those. Now we can also take other roots other than square roots. We can take cube roots. Cube roots are solutions to the equation x cubed equals b. Every number b, whether it's positive, negative, or 0, has exactly one real cube root, which was not the same for square roots. Positive numbers had two real square roots. Negative numbers had no real square roots. 0 has one real square root, and it's itself 0. But every number b has exactly one real cube root. We call that the cube root of b. The cube root of a positive number is positive, the cube root of a negative number is negative. So the cube root of 8 is 2, because 2 to the third power is 8. The cube root of negative 8 is negative 2, because negative 2 to the third power is negative 8. So the cube root of negative 64 is going to be the number that I multiply by itself 3 times to get negative 64. Well, that's going to be negative 4, since negative 4 cubed equals negative 64. It would be negative 4 times negative 4, which is positive 16, times another negative 4, which is negative 64. Example B, the cube root of 10 to the 6th. So that's going to be 10 squared, because 10 squared to the third power equals 10 to the 6th. So the cube root of 10 to the 6th must be 10 squared. It's what I raised to the third power in order to get 10 to the 6th. So 10 squared is 100. So the cube root of 10 to the 6th is 100. So 100 times 100 times 100 would be 10 to the 6th. The cube root of a to the 9th, well, what number am I raising to the third power to get a to the 9th? That must be a to the third. So the cube root of a to the 9th is a to the third. We can also take higher roots, like fourth roots and fifth roots, etc. We'll generalize those and call those nth roots of b. And an nth root of b is a solution to the equation x to the n equals b. If n is 2, the nth root is really just the square root. If n is 3, the nth root is the cube root. And so we know how to do both of those. And we can glean from those information about higher order roots. Turns out, the same thing is going to happen for all even powers, and the same thing is going to happen for all odd powers. So for all even roots and for all odd roots. If n is even and b is positive, there are 2 real nth roots of b. Just like when n was 2, there were 2 real square roots for a positive number. And we call the principal one, or the positive one, the nth root of b. The other one is negative the nth root of b. If n is even and b is 0, there's one nth root, and that's 0. The nth root of 0 is always 0, because 0 times itself any number of times stays 0. If n is even and b is negative, there is no real nth root of b. Just like there are no real square roots of negative numbers. If n is odd, there is exactly one nth root of b, whether b is positive, negative, or 0, and we saw that when n was 3. We took cube roots. So let's simplify that. Fourth root of 81. What number raised to the fourth power equals 81? Well, if you think about it, it's 3. 3 to the fourth power is 81. So 3 is the fourth root of 81. What's the fifth root of 32? What raised to the fifth power equals 32? 2. The fifth root of 32 is 2. What is the sixth root of negative 1? Well, 6 is an even number, so I cannot take an even root of a negative number. So this is no real solution. No solution in the real numbers. We call any number involving a root, whether it's a square root, a cube root, etc., a radical. So the nth root of b is a radical for any number n and any number b. So you've got 9 radicals there that you need to simplify. Simplifying radicals is much easier with these properties. The first property is that the nth root of a product of two numbers is simply the product of the nth roots. So I can walk through an example here with the square root. The square root of 4 times 9 is the same as the square root of 4 times the square root of 9. Because the square root of 4 times 9 is the square root of 36, which is 6. The square root of 4 is 2. The square root of 9 is 3. And 2 times 3 is 6. So I can multiply them and then take the square root, or I can take the square roots of each one and multiply those two numbers, and I'll get the same thing every time. Similarly, the square root or the nth root of a fraction is the nth root of the numerator over the nth root of the denominator. This is not true if we are adding or subtracting underneath the radical. The square root of 9 plus 16, which would be the square root of 25, which is 5, is not the same as the square root of 9 plus the square root of 16. I cannot split it up if I'm adding or subtracting underneath the radical. But if all I'm doing is multiplying and dividing, I can split it up. So here are some examples. Simplify the square root of 98. Well, the square root of 98, I know that 98 is 49 times 2. And I'm going to split it up like that. Why like that? Because I happen to know the square root of 49. What is the square root of 49? Well, it's 7. So I can replace the square root of 49 with 7. So the square root of 98 is the same as 7 square root of 2, or 7 radical 2. The cube root of 25 times the cube root of 10, that's the same as the cube root of 25 times 10, which is the cube root of 250. Okay? Well, that's not simplified if there is a number I know the cube root of that goes into 250, and there happens to be one. I happen to know the cube root of 125, and 250 is 125 times 2. So this is really the cube root of 125 times the cube root of 2. What is the cube root of 125, you ask? Well, it's 5. So this is 5 times the cube root of 2. So we keep going until we cannot break up the root into numbers that we know the root of anymore. So example C, the cube root of 81 over 8. I can take a fraction and I can split it up into the cube root of the top over the cube root of the bottom. Okay? Do I happen to know the cube root of 81? Well, I don't, but I know a number that divides into 81 that I do know the cube root of. 27. 27 goes into 81 and does so 3 times. So this is really the cube root of 27 times the cube root of 3. Do I know the cube root of 8? That I do know. 2 times 2 times 2, 2 cubed, is 8. Okay, so I keep going. The cube root of 27 is 3, so I replace that with a 3. Then I've got a cube root of 3 all over 2. Square root of 60 over the square root of 5. Well, I can combine that as the square root of 60 over 5. And why should I do that? Because 5 goes into 60. How many times does 5 go into 60? It goes in 12 times. So I've got the square root of 12. Alright? Is there a number I know the square root of that divides into 12? 4 does. This is the square root of 4 times the square root of 3. Okay, and I can take the square root of 4, and that's 2, so I replace it with 2, and I still got a square root of 3. Example E. Square root of 2a squared b. Okay? Well, I can split that up as the square root of 2 times the square root of a squared times the square root of b. Do I know the square root of 2? No. Do I know the square root of a squared? Yes, that's a. Do I know the square root of b? No. So the 2 and the b have to stay underneath, and I took the square root of a squared, and it comes out as just a. So I write it in front. Example F. The square root of 36w cubed. Well, that's the square root of 36 times the square root of w cubed. Okay, the square root of 36, I know, that's 6. W cubed, I can always split that up as a w squared times a w, right? And I know the square root of w squared. The square root of w squared is w. So this is 6w times the square root of w. So if I'm taking the square root of an odd-powered variable, I can take out the even-powered, leave myself with one of them, and take the square root of the even-powered one. So we'll see that again here in example G. The cube root of x to the 5th over y cubed. So I'll rewrite that as the cube root of x to the 5th over the cube root of y cubed. Okay, the bottom's easy. The cube root of y cubed is just y. On the top, the cube root of x to the 5th, well, that's the same as the cube root of x to the 3rd times the cube root of x squared, right? I can take x to the 5th and split it up as x cubed times x squared. Alright, the cube root of x cubed is x. Still got a cube root of x squared. Can't do anything more with that. And I've got a y on the bottom. h, the square root of 4a squared plus 4b squared. Well, I'm adding underneath there, so I can't split it up. But there's a 4 in both of those. I can factor that out. Okay? Square root of 4 then is 2, and I'm left with the square root of a squared plus b squared. Again, because I'm adding underneath the square root, I cannot split it up. That is not the same as the square root of a squared plus the square root of b squared. So fundamentally different things. Okay. A radical expression is not considered simplified if there is a radical in the denominator of a fraction. We do not like having radicals of any form in the denominator of our fractions. So we get rid of them from the denominator. And we do so via a process that's called rationalizing the denominator. Rationalizing the denominator means multiplying the whole fraction by 1, because multiplying anything by 1 doesn't change it, so I'm allowed to multiply it by 1, but I'm going to do so in a creative way, a way that manipulates the way the fraction looks. So here's how to do it. Let's take the square root of 5/3. That's really the square root of 5 over the square root of 3. I can't simplify that because I don't know the square root of 5 or the square root of 3, and I don't have any smaller numbers that divide into 5 and 3 that I do know the square roots of. But I have a square root in the bottom of the fraction, and I hate that. That is ugly, abhorrent. I want to get rid of that, so I rationalize the denominator. And here's how I do it. I multiply my fraction by 1, but 1 in the form of square root of 3 over the square root of 3. So I'm multiplying by 1, it's not changing the fraction. But multiplying by the square root of 3 over the square root of 3 means on the top I'm going to have the square root of 15, 5 times 3, over the square root of 3 times 3, or the square root of 9, which is 3. So I've magically gotten rid of the square root in the bottom. And it's just a regular 3. And that's considered more simplified than what we started with. Part B. 4 over the cube root of x. Okay? So 4 over the cube root of x. Here's how I do it when it's not a square root. I'm going to multiply by the thing that will make it a perfect cube on the bottom. So I'm going to have to multiply by the cube root of x squared. And you'll see why in a second, rather than just the cube root of x. Notice, by the way, that I'm connecting each step with an equal sign, because I'm simplifying an expression. You're doing that too, right? So at the top I have 4 times the cube root of x squared. On the bottom I've got the cube root of x times x squared, which is x to the third. So by choosing x squared, I've gotten x to the third, which I can take the cube root of and get x. So I've got 4 cube root of x squared over x. Can I cancel that x into the x squared? No, because the x squared is trapped underneath the cube root, while the x on the bottom is free. So I cannot throw it into the cube root on the top. It's outside and it's not going back in. So radicals are in simplest radical form if the number underneath the radical has no factors that are perfect nth powers other than 1, and every denominator has been rationalized so that no radicals are in the denominators of fractions. Assume that if your instructions are to simplify, that you are putting them in simplest radical form. All of the problems I've done so far, I put my answers in simplest radical form. So you've got several examples to do. Part 3, sums of radicals. So we can only add or subtract radicals if they are like terms. What makes two radicals like terms? Well, two things. They need to have the same radicand. They need to have the same number underneath the radical, the same number underneath the root. For example, 3 radical 2 and negative 5 radical 2 are like terms because they have the same number underneath the root. They have the same radicand. But 4 radical 5 and 3 radical 7 are not like terms because the 5 and 7 are not the same. Secondly, they also need to be the same type of root. They need to both be square roots or both be cube roots or both be sixth roots. They have to be the same type of root or they're not like terms. So once you have like terms, you can add them together using the distributive property kind of in reverse. So here's some examples. Let's simplify the square root of 8 plus the square root of 98. Well, those do not have the same root. But can we transform them so that they do? Well, the square root of 8 is the square root of 4 times the square root of 2. And the square root of 98 is the square root of 49 times the square root of 2. Which means this is 2 radical 2 plus 7 radical 2. Now they have the same root. And I can add the numbers in front. 2 plus 7 is 9. So now I've got 9 square root of 2. I had 2 root 2's, then I added 7 more root 2's, made 9 root 2's. And that's simplified. Example B. The cube root of 81 minus the cube root of 24. Again, they don't have the same radicand, but I can make them have it because 81 happens to simplify nicely to the cube root of 27 times the cube root of 3 minus 24 is the cube root of 8 times the cube root of 3. Why did I choose 8? Because I know the cube root of 8. And I know the cube root of 27. That's 3, so this is 3 cube root of 3 minus the cube root of 8 is 2. So 2 cube root of 3. So the more you do this, the more you'll remember and recognize the numbers that you know, the square roots of and the cube roots of and the fourth roots of. So I've got 3 cube roots of 3 minus 2 cube roots of 3. That'll give me 1 cube root of 3. But I, of course, don't need to write that 1 in the front, because multiplying by 1 doesn't change anything, so this is just the cube root of 3. Example C. Square root of 32 over 3 plus square root of 2 over 3. Okay? I can rewrite this as the square root of 32 over square root of 3 plus the square root of 2 over the square root of 3. Right? And then I can write that as one fraction. Square root of 32 plus the square root of 2 over the square root of 3. Square root of 32 is the square root of 4 times the square root of 8, or, better yet, it's the square root of 16 times the square root of 2. And I know the square root of 16 is 4, so it's 4 root 2 plus a root 2 over a root 3. Okay? That makes 5 root 2 over root 3, or 5 radical 2 over radical 3. Part D, example D. Radical 6 times radical 2 plus radical 3. Well, I can distribute the radical 6 into the parentheses and get radical 12 plus radical 18. Radical 12 is radical 4 times radical 3, and radical 4 is 2, so this is 2 radical 3. Radical 18 is radical 9 times radical 2, so that's 3 root 2. Do they have the same radicand? No. Are they completely simplified? Yes. So I know that I can't add them together or simplify them any further, and I'm done. Part E. Square root of 21 plus the square root of 15 over the square root of 3. Okay? Well, I can take the 3, the square root of 3, and I can split this into two fractions, square root of 21 over the square root of 3 plus the square root of 15 over the square root of 3. Okay? Square root of 21 over the square root of 3 is the square root of 21 over 3. Square root of 15 over the square root of 3 is the square root of 15 over 3. Combining them into one radical like that allows me to divide the numbers underneath. And 21 over 3 is 7, so this is the square root of 7. Plus 15 over 3 is 5, so it's the square root of 5. Those are both simplified all the way. They don't have the same radicand, so I can't combine them any further. Example F. Square root of 12x to the 5th minus x square root of 3x to the 3rd plus 5x squared square root of 3x. There's a lot going on there. Let's simplify each one individually. Square root of 12x to the 5th. 12 is 4 times 3. I know the square root of 4 is 2, so I'll bring the 2 out front, and I still have the square root of 3 underneath. The x to the 5th, well, I'll do this in pieces for you. X to the 5th I can do as the square root of x to the 4th times the square root of x. Okay? Minus the square root of 3 I can't do anything with. But the square root of x cubed I can rewrite as the square root of x squared times the square root of x plus 5x squared square root of 3x. Can't do anything with that. It's already broken down as far as it can go. Alright? Next. I've got the square root of x to the 4th. That is going to be x squared, because x squared times x squared is x to the 4th. So I can bring an x squared out front with my 2. I still have a 3 and an x underneath, so I'll write them together. Okay, minus I can take the square root of x squared and get x. Bring that out front with the x that's already out there. Makes x times x, which is x squared. Still have a 3 and an x underneath. Plus, this one still can't change, 5x squared times the square root of 3x. But hey, now I've got 3 terms, all of which have the same radicand. So I can add the numbers in front. Okay, I've got 2x squared minus x squared plus 5x squared. That's 6x squared times radical 3x. So I've manipulated them until I got the same radicand, and then I could add them together. Now you have some problems to do just like that. Part 4, binomials containing radicals. So we just dealt with adding and subtracting radicals. Now we're going to deal with multiplying them as binomials. We multiply binomials containing radicals by FOILing them, just as we normally would if we didn't have any radicals in them and just had numbers and variables. So we FOIL. So we're going to take 4 times 3, and that's 12. We'll take 4 times 2 radical 7, and that's 8 radical 7. We'll take radical 7 times 3, and that's 3 radical 7. And we'll take radical 7 times 2 radical 7, which is 2 times radical 49, which is 7. Okay, so I've got 12 plus 2 times 7 is 14, so the 12 and the 14 makes 26, plus 8 radical 7 plus 3 radical 7 makes 11 radical 7. So I FOIL it and I combine like terms, just like normal. Example B, 2 radical 3 minus radical 6, quantity squared. Does that mean I can take 2 radical 3 squared minus radical 6 squared? No, because squaring something is multiplying it by itself. So I need to multiply this binomial by itself and FOIL. So 2 radical 3 times 2 radical 3 becomes 4 times 3, which is 12. 2 radical 3 times negative radical 6 becomes negative 2 radical 18. Negative radical 6 times 2 radical 3 becomes another negative 2 radical 18. And then negative radical 6 times negative radical 6 becomes positive radical 6 squared, which is positive 6. I've got 12 plus 6, and that's my 18. And then negative 2 radical 18 minus 2 radical 18 is negative 4 radical 18. But the radical 18 I can simplify as radical 9 times radical 2, and I know radical 9 is 3, so this is times 3 times radical 2. So 18 minus 12 radical 2. So I FOIL, and I combine like terms and simplify. Example C, 4 radical 5 plus 3 radical 2 times 4 radical 5 minus 3 radical 2. We FOIL. 4 radical 5 times 4 radical 5 becomes 16 times 5. 16 times 5 is 80. Then I've got 4 radical 5 times negative 3 radical 2 becomes negative 12 radical 10. I've got 3 radical 2 times 4 radical 5, which becomes positive 12 radical 10. Then I've got 3 radical 2 times negative 3 radical 2, which becomes negative 9 times 2, which is negative 18. Combine like terms, but hey, those two middle terms cancel. They're the same except opposite signs. That leaves me with 80 minus 18, and that's just 62. So I just got a standard number, no radicals. And that happened because the two binomials I started with were the same except for the sign in the middle. That makes them what are called conjugates. And anytime we multiply two conjugate binomials together, the middle terms after we FOIL always cancel, because they always end up with the opposite signs and otherwise are the same. And that just leaves us with the two numbers on the ends, which are always whole numbers, and we'll combine to make a whole number. So multiplying two conjugate binomials will always give us a whole number. We can use that then to our advantage to rationalize the denominator that contains a binomial. In order to do so, we multiply by the conjugate over itself. So we're still multiplying by 1, just like we did when we were rationalizing the denominator earlier. But this time we multiply by 1 as 3 plus radical 5 over 3 plus radical 5. That is the conjugate of 3 minus radical 5. Doing so is going to give me only a whole number on the bottom because the radicals will cancel. So multiplying this means I FOIL. FOIL the numerators, FOIL the denominators. So in the numerator, I've got 6 times 3, that's 18, plus 6 radical 5, plus 3 radical 5, plus radical 5 times radical 5, which is 5, over 9 plus 3 radical 5 minus 3 radical 5 minus radical 5 times radical 5, which is 5. So on the top, that gives me 18 plus 5, or 23, plus 6 radical 5 plus 3 radical 5 is 9 radical 5, over 9 minus 5 is 4, and the 3 radical 5 and the negative 3 radical 5 cancel. That's what I wanted to happen. That's why I multiplied by the conjugate, so that that would happen. And thus that leaves me with only a whole number on the bottom. And I am done. And then you've got 3 more problems to do, and then you're done. And that is the end of this video.